Hello, dear students. Hope you'll be fine. Today I am going to start now the third lecture on this tensors. And in previous lecture, तो हमने जो हमारा previous lecture था lecture number 2 वहाँ पे हमने discuss किया था how we can define the duals of duals. So that means if you take the variation of a vector with respect to a scalar, or second if you take a variation of a scalar with respect to a vector. So both are vectors and these are called duals to each other, right? So this was our lecture number 2, and today we are going to discuss about Euclidean vectors with coordinates, right? तो मतलब इससे पहले in one of the lecture हमने define किया था कि these Euclidean vectors without coordinates, right? So simply we define that vector and scalar. Then we say how we make the coordinate transformation. So with the help of that coordinate transformation, how we can define this as scalar, right? So this is how you can relate scalar with the tensors, right? Because tensors transform like that, right? So that means the definition of this scalar, it resembles that definition of tensors when you make the coordinate transformation, when you are going from one plane to another plane, right? So coming back to our main topic, so today's topic is that's Euclidean vectors with coordinates, right? So that means if we talk about now in three dimensions Euclidean space, so that means if we have a three-dimensional Euclidean space where I, j, and k are the unit vectors along that x, y, and z direction, and this is our this 3D Euclidean space, right? Okay, and we can define that. So these unit vectors, they have some property. So that is that I dot I, that's equal to 1. So that means the because these are at right angles to each other, right? So these are normal to each other, right? Because A dot B will be equal to, yeah, maximum value, because angle between these are 90. And second property that we have that right? So first property tells us that these are normal to each other, right? So this scalar product between same, so that's equal to 1, because that purely gives you the length, right? Purely a scalar, I mean to say, right? And similarly, when you take the dot product with different these unit vectors, so that's equal to 0. So that means this property says that these are mutually orthogonal. And this one says that these are at right angles to each other, right? So that means if you add these two properties of these unit vectors, they are saying that these are called the orthonormal unit vectors, because unit vectors, because they have that the magnitude of that, the length of that unit vector is 1, right? So this, it simply gives us the direction along that all the x, y, and z direction. If you talk about the three-dimensional space, right? So that means, so we can say that these unit vectors are called orthonormal. Okay, so these unit vectors are called orthogonal. So let us change now the notation, because I need to generalize my equation. I need to generalize if we write it for any vector. So I will generalize it. So I can write now. I will suppose here that our this. Let us choose now. Okay. So simply these are again unit vector. I am changing the notation from ijk to, in order to generalize it, in order to write it in some compact form. So the condition of that orthonormality, so I need to write it in some compact form. So I can write that our this. Okay, so that means you take the dot product between the vectors, so that's equal to this or that canonical delta, right? And this n and m, right? So that means this canonical delta has some properties that, so this delta n, so this is equal to 1. So that means if n is equal to m, so we can have its value will be equal to 1, or it is equal to 0 else. So that means if n is not equal to n, right? So if you give, so I'll give some examples. So this is the orthonormality condition of these unit vectors. So you can take the different values of that n and m. Suppose I will take that if n equal to 1, m equal to 1. So that means, so that's equal to, right? So that means if n is equal to m, so the value of this canonical delta will be equal to 1, or you can write that putting n equal to 1, m equal to 1, so even dot even, because even is that first ith component, so that's I dot I equal to 1. And similarly, if you put that n equal to 1, m equal to 2, so you can have that even e2, so that is equal to I dot j, that is equal to 0. So that means then n is not equal to m, because अभी हमारा जो n है that's equal to 1 and m equal to 2. So that means you are taking that I dot j. So that means but these are mutually orthogonal to each other, right? So you can say that when n is not equal to m, so its value will be equal to 0. So this is how you can write this that orthonormality condition in some compact form. So that's why इसलिए मैंने इसको change किया from some I j k into in terms of that e1, e2 and e3. Okay. Now, in addition to that, so we can say that अगर हमारे पास कोई vector होगा, if you take any vector, so that can be written as a superposition of if you have any vector in space, you can write the superposition, linear superposition of these unit vectors. अगर हमारे पास एक vector, if we suppose some position vector, if you consider some position vector in three-dimensional space, suppose we have some position vector here R, right, and it can be some, it's some space that's x, y, and z. So this position vector, you can write it in terms of these superposition of these unit vectors plus that component, right? So let me write. So we can write now. So we can write then if we have any position vector. Suppose I consider some position vector. So R will be equal. That's equal to, right? So that means, so any vector can be written as a superposition of these linear combination of these vectors, right? And so or you can write it in some compact form. So similarly we can write it अगर हमारे पास कोई वेक्टर होगा in some three dimensional space, तो हम इसको लिख सकते हैं as a superposition or linear combination of these unit vectors, right? Plus those components along that x, y, and z, right? So that means if I write now, I will choose now. So suppose our x is our x1. Okay, so you can write that. Okay, or instead of that, you can write this as so you can write this as summation over. Right? So it hardly matters. You can put this I in the subscript or you can put in a superscript. So it has nothing to do with. So we'll discuss that about that contravariant and covariant. but this it has nothing. So it only takes those first, second, and third components. So that means our E1 corresponds to our I component, and E2 corresponds to J, and E3 corresponds to K component, right? And this is how we can write this position vector in that three-dimensional Euclidean space, right? So that means अगर हम if I write some, so for any vector, if we write for any vector A, अगर हमारे पास एक वेक्टर A होगा, so we can write that vector A as okay, because when you take that, or you can write this as, if you take, so this is that A1 E1, right? Or you can write this as our A vector will be equal to sorry. So this is how you can write a vector. So that means you are writing some vector in that 3D Euclidean space. That's x, y, z, and we have some vector A here, right? And we can write this as the linear combination of those different components of that vector A along that x direction, y, and z direction. Okay. So we can write, so that means a set of vectors. If we have set of vectors, in terms of which all other vectors can be, all other vectors in the space can be this expressed by the superposition. So that means अगर हमारे पास set of vectors होंगे, so in terms of which, तो अगर हमारे पास कोई vector होगा in that space, if I write that vector in terms of these linear combination of these set of vectors, right? So those set of vectors are called, these are called bases, right? So if we define now the basis, so basis is simply that we can have a set of vectors, like if I have these orthonormal unit vectors. So if I write now, if I have the set of vectors in some space V, and if you represent some another vector in terms of the linear combination of these set of vectors, then these set of vectors are called bases. And one more important condition for this these bases is that they should be linearly independent and they should span the space, right? So, so one more important criteria is that they are linearly independent and they should span the space, right? So this is how you can define those basis vectors, I can say. So that means like, well, okay, I will come to that point. So that means if you have set of vectors, if any other vector can be represented as a linear combination of these set of vectors, where set of vectors A, B, C. If I write another vector D in terms of that A plus B plus C, then these A, B, C are called the bases, right? And one more important criteria is that those bases, they are linearly independent and they span the space. So span the space, you understand that if we have this, so that means the vectors can be then any vector can be written as the superposition of basis vectors, right? So that is how we can define this. So if I have some space V, so you can represent some vector in terms of the superposition of these set of vectors, right? So we can say that that vector basically span the space, right? If I represent that vector in terms of these linear combination of these vectors, set of vectors, so we can say that that vector spans that particular space, right? And one more this condition is that they are linearly independent. So that means अगर हमारे पास if we have set of vectors, right? So suppose we have three vectors, we have that u, v, and w. These are three vectors. So you can write that, if you write that AU plus equal to 0 and equal to 0, right? So this is, you can say that these vectors UV and W, these are called linearly independent, provided that these constants A, B and A should be equal to B is equal to C, that should be equal to 0. Or you can say that, what about those unit vectors? We are saying that these are orthonormal unit vectors. Can these unit vectors can be these basis vectors? So they might be, right? Because those basis vectors, as I already explained you how you are define the basis vectors, plus they are linearly independent, and so that means they are linearly independent and they should span the space, right? So that means here, if you write now, so you can say that these unit vectors, we have these unit vectors along with that I, J, and E. So we can say that these unit vectors can act as a basis vectors, or because it fulfills this criteria, right? So ये criteria fulfill करता है, because we can say that we cannot write this I vector as a linear combination of this J and K vector. I can't write this I vector in terms of this linear combination of J and K. So that means these three unit vectors are linearly independent, and they also span the space, because I can represent anything in terms of the linear combination of these set of vectors. So that means I can write these basis vectors, these unit vectors, I can represent as basis vectors, right? Sometimes, because these unit vectors have dimensions, their magnitude is equal to 1, their length is equal to 1, right? So we can say that, so I can represent now, let me write now, if I have, suppose अब हमारे पास एक वेक्टर है जो मैंने आपको ऑलरेडी बताया कि और वेक्टर इज सम, दिस इज सम x y and we have some vector a here, right? Okay, so this vector is known to us. So I'm saying now, if our vector is that a vector equal to, that's equal to summation over I. Okay, so this is how you can represent, because or you can write this as, okay, so this is how you can represent this vector. तो ये हमें ऑलरेडी पता है, right? Now if you want to calculate, हमें पता है कि we know that what is vector A, and we need to calculate, so we want to find that this value of this vector A along the x, y and z direction. So that means we need to calculate their projection. So projection of this vector A along x, along y and along z direction. So we can simply take it this, अगर इसका मैं कोई component calculate करूँगा along x or y or z direction, so I need to multiply this vector by e1, right? So if I multiply this vector by e1, that basically gives me the component of this vector A along x direction, right? And similarly, if I take the product of that vector A with this unit vector that's along that y direction, because our unit vectors are now e1 and e2, right? So मैंने आपको ऑलरेडी बताया कि why I am changing this notation, because I can write that condition for this condition for that orthonormality. So in order to write it in that form, तो इसलिए मैंने इसको change notation किया. Instead of that IJK, I am representing by E1, E2 and E3. So we can generalize it then. Right? So this is very clear. Now, तो what we can, so अगर मुझे कोई component अब निकालना हो, क्योंकि मेरे पास vector A पता है, so you want to calculate any component of this vector A along x, y and z direction. So that means you want to calculate the vector A, the projection of this along x, y, z direction, right? So we can simply calculate by taking the product of this vector along with this E1, that gives you the x component, and similarly if you take the product of the scalar product of A vector with this y, this gives the projection on y, and similarly for z direction, right? So I can rewrite this. So this will be equal to A dot AI, right? Or this will be equal to, let's say, AX. So dot with E1, right? Because I take that A dot E1. So that's equal to, because now AX with dot product with E1 dot E1, that's equal to 1, right? And this will be AX. And second component will be when you take AY with E2 with E1. So that's equal to 0. Because we have that, okay, let me write this. Because we know that using the condition of orthonormality, right? Because we have that, right? So because here n equal to 1, m equal to 1, so this is equal to 1. So we can have this. This will be simply AX into 1, right? And these terms will be 0. Because A2 with A1. So that means knowing the vector, if we know this vector A, so we can calculate what will be the value of this vector A along that x direction, so that you can simply take this product with this unit vector along x, and similarly you can write for so we can write them. So our A vector dot E1 equal to AX, right? And okay. Now in addition to that, we can so let us now represent these unit vectors. So because we have this condition, so we have this condition that En dot Em equal to delta N. So we can replace this En cap by En vector. So that means uh, I am replacing this unit vector by this basis vector. So these are basis vectors. These are not the unit vectors. So these are not, so these are basis vectors because they fulfill the criteria for these bases. So as I already mentioned you, so how we can define the basis? They should be linearly independent and they span the space. Both of these conditions are satisfied by these unit vectors. So that means I am replacing this unit vector by these basis vectors. So that's why you can put an arrow here, right? And there was cap, so this was unit vector. Now this is a basis vector. So that means I can have this orthonormality condition for these basis vectors also, right? So I can write them for En, right? So this is again our chronicle delta, but its form is, so we can have this delta N equal to 1. Yep. And this delta N, okay? So that means this delta N, if you talk about in three-dimensional space, so it can have, so first component corresponds to our 1 1. So this corresponds to 2 2, this corresponds to 3 3. So that means we can have that even dot E1, so that's equal to this one, or E2 dot E2, that is this one, and E3 dot E3 will be equal to this one. Rest, if you take E1 dot E2, so that is this one, so that is 0 because n is not equal to n. So this corresponds to that canonical data. If you talk about, you can write in determinant form, right? Now, in addition to that, if you take now, because we have generalized this, we can write this in terms of these basis vectors because we know that. तो हमने already explained किया था because we can write this. We have written this a vector can be written as so that's equal to that summation I starts from 1 to 3 ai, right? Okay. You can, because if you change this now ai to, sorry, a bit mistake. Okay, so let me clear this. So we can write now pi. I am changing it by the basis vector, right? So I can write then vector a will be equal to, so summation over pi, right? Now we can see from this. So this is how we can express this vector in terms of the basis vectors. Now if you take the product of two vectors now, right? Suppose we have two vectors, a vector and b vector, and this is some summation n starts from 1 to 3 a and b equal to, okay. So simply मैंने क्या है, so I am expressing this vector in terms of this and b vector in terms of this. Now if you take the dot product between them, तो अगर मैं यहाँ पे डॉट प्रोडक्ट इन दोनों का निकालूंगा, so that is a dot b. Or okay, so let me write here because I can write what's all a dot b here. Okay, because if you remember that, because we have defined a, हमने ऐसे define किया, that is summation n starts from 1 to 3 a n e n cap, not e n cap, sorry. So you write now, because I am writing it in terms of the basis vectors, so we can represent it in vector notation. So this will be this one and the other. Okay, so this is a and b, right? And now because a is this one and b is this one, now you take a dot b. So a dot b is that is equal to okay, so again I did a mistake here. Okay, so this will be, now we can write now, so this will be equal to, okay, because you take it because these are vectors, they are simply the magnitudes, right? Take the dot product between these two vectors. these two okay, these vectors I mean to say. You can write this as, so this will be okay. Now this is very clear. So that means if you take the dot product between the vectors, so you can write it in terms of that n comma m, or you can write two summations like this. So ऐसे भी हम लिख सकते हैं, both running from 1 to 3, right? So first corresponds to 1 is x component, 2 corresponds to y, and 3 corresponds to z component, right? Now this is a and b, so that means if n equal to m है, तो यहाँ पे अगर मैं n m के बराबर होगा, so that means this is a dot a. So this will be that. So that gives me the which component. So I can write here. So that means I can write that our a dot b is a dot b. So that is equal to summation over. So that's equal to. So that means if n equal to m. So we can have that a dot b will be equal to. Right, because this delta n will be equal to 1 here, n is equal to, so जब n m के बराबर होगा तो a dot b will be this one, right? So what does it indicate? Because if you remember that delta n m, so that is that 1 0 0, right? So ये हम different components के ले रहे हैं conical delta, right? Now if n equal to because this is a n dot b n, right? So this is a n dot b n. So this is b n because n equal to m. तो यहाँ पे अगर मैं n का वैल्यू 1 लूंगा, so if I put now n equal to 1, so that means our a dot b will be, so that will be equal to a1 dot b1. So that is equal to ax dot b. तो ये जो हमारा कौन सा कंपोनेंट होगा, so that corresponds to this because n equal to m, so that is equal to this one. And similarly if you put n equal to 2, so that a dot b will be, so that will be equal to ay dot by, right? So that means this will be that you can calculate. So what will be that a dot b here? So this gives us that this when you take the product between the two vectors, but in terms of these basis vectors, right? So because time is limited, maybe in the coming lecture I will discuss about that using the same notation of these vectors, how you represent these vectors in terms of these basis vectors, right? Basis these vectors, right? And if you take now the cross product between the vectors, how we can represent that? So maybe hopefully next lecture we'll discuss that. Thank you.